Hello, everyone. Thank you for coming to my talk. My name is Qian. I'm from MovieLens, University of Minnesota. I'm going to present a paper, prediction for recommender systems. And this is a collaboration with a PhD student, Shuo Chang, who recently graduated from our lab, and research scientist Max Harper, and Zhao Konstan, my advisor. So first of all, why gaze in recommender system? So I'm going to show you a short video clip. I hope it works. And this is a user using MovieLens with their eyes being tracked. And there's a red dot you see there, big dot, those are fixation. And the lines, red line, that's saccade. So this user look at the first row and take several fixation, look at the last movie, Bad Santa, and decide to take that one. And this almost skip the second row. And they go to the third row and look at the movie called Lemonade Snake, and decide not to take that. So the point here is actually users are thinking a lot. And beyond what is normally logged in browsers, like logged readings and actions, users are thinking, and we cannot log that. And we really want to understand what is in users' mind and what users are thinking, go beyond readings and actions. This has been studied a lot by researchers looking at decision-making and choice-making research and cognitive modeling. They employ this kind of technique, such as process tracing technique with eye tracking. And, but interesting, in recommender system mostly as a decision supporting tool, we haven't looked at a lot on this yet. And another reason to look at gaze is to better understand the user in action. What I mean by in action is, I think this topic has been mentioned a couple of times in this conference, is when a user skip some items. So we present a bunch of recommendations to the user picks some of them, clicks some of them, but skip all the rest. So what can we say about those items? Do users see those items at all? And machine learning algorithms, recommender system based on machine learning, they made a bunch of assumptions. For example, if you build a recommender based on binary implicit feedback with actions as positive, no actions as negative. So the question we want to ask, are those positive training instances really positive? This is related to the well-studied position bias in information retrieval community. So that it basically says if a user clicks the first one in the search results, it doesn't necessarily mean it's the best one. And because by design, it is biased to have higher clicking probability. And also the second question, similarly here, are negative training instances really negative? And what if the user doesn't see that item at all? Should we penalize those items for continued display in the future? With eye gaze data, we can answer those questions. However, eye tracking currently is not widely used. And even in the near future, it may not be widely used with advanced eye tracking type technology like portable eye tracking technologies. And even further, eye tracking may not be widely used at all because of the privacy concerns we have. We do not need that. We do not want such a low-level tracking on us. So why not first model and predict gaze? And this is what this research is about. And we particularly focus on this grid-based interface, which is widely used in recommender system. For example, YouTube, Hulu, Google Apps, and also MovieLens in the bottom right. So as researchers have studied in attention or visual attention prediction, it's a really hard problem. As I showed previously, those scanning paths, fixation, dots, and the saccades, those are really hard problem. So we turn to a simpler one, but this simpler problem might be useful for recommender system. We call this aggregated fixation prediction. Consider a user is browsing a page, just one page view, in a grid-based interface, R rows and C columns. And we want to ask, aggregating the entire page view to predict each displayed item's fixation probability. That is, what is the probability that this user has ever been fixated on that page view, aggregating? And what is the total time of fixation on that item, on that position? And given the user's browsing data, for example, item positions, we use page dwell time and user actions. And this probably you could call it a gaze inference problem instead of prediction because it happened in the past. We know the user browsing data, and we want to infer where the gaze is. And you may also notice that we do not use saliency, which is a bottom-up approach in attention theory. And we take this top-down approach. For detailed comparison between these attention theories, please go and check the paper. And for now, we are going to talk about this top-down approach. There are two scenarios here. We can basically train a model only based on user browsing data. However, we can also collect some eye tracking data from a small number of users to improve. This is important. Collecting this eye tracking data is important because of two reasons. First of all, we want to evaluate. If we do not have eye tracking data, if we do not have ground truth, we don't know how well we are predicting. And the second one is we want to ask whether this gaze prediction can extrapolate across users. Can we use some users' gaze data to predict other users? This is important for the scalability of this approach. So given that, we use two data sets, MovieLens. One is 1 month of user browsing data. This gives us 100 page views, 100,000. Then we collected 17 subjects' eye tracking data, with each recorded for 30 minutes. And this gives us 10,000 data points. By data point, I mean each movie display, item display on the page. And we ask the users to do a bunch of tasks. And for detailed procedures about this eye tracking data collecting procedure, please go and check the paper. So first of all, we start from a simple approach, which is building linear models. This is only for the scenario that you have eye tracking data. This is a supervised learning model. We build a logistic regression for fixation probability, and build a hurdle linear model for fixation time because of the zero inflation property in the data set. And this hurdle linear model basically is a two-stage modeling process. The first model, the zero, or non-zero, as in like logistic regression, then build another count model on top of the data. We use 3 types of features: position feature, row index and column index, dwell time. And the third type of feature, 1 over mean action days. This encodes the insight that if we know that a user click a position or do something with that position, probably the probability of fixation probability surrounding that position will be higher. That's the insight and intuition. And given this, you might be reminded that this could be encoded by Bayesian inference. If we are willing to make an assumption about the likelihood function, given the fixation variable and the likelihood function of the action, we probably could do Bayesian inference about the posterior of the fixation. And this is exactly what HMM is doing, Hidden Markov Model. We directly apply Hidden Markov Model here for this scenario, but it takes several tricks to make this work. First of all, different from the previous work on attention modeling in cognitive research, this latent variable is not a user's state of mind. This latent variable is just fixation. And the observed variable is action. So there are 2 sets of variables here: fixation variable F, action variable A. So for each page view, we split that total page dwell time into constant time intervals. And for each interval, there are 2 variables associated with it: is fixation variable, action variable. And this time interval is the parameter to tune. So we need to pick the best one. So the fixation can take R by C possible values, which is the total number of positions on the screen, and action can take R times C plus 1. 1 is no action at all. So estimation, it's if we have eye tracking data, we want to estimate the initiation vector alpha, transition matrix T, and emission matrix E. We can just do a maximum MLE and to estimate the eye tracking data, maximum likelihood estimation. If we do not have eye tracking data, F is latent, we can do EM algorithm. but it turns out that this is actually worse than a simple approximation. Approximation basically means you approximate fixation directly using the action. You just treating action as a fixation and estimate alpha and t. And it works. I will show you the results in a minute. The prediction based on this model using the posterior of F. It's a marginal distribution. You can check the paper for details. So evaluation, we pick 20% of the 70 subjects for testing, others for training, and repeat 100 times, but always use a different set of testing subjects to ensure our measurements are independent with each other for testing purpose. This is the first set of fixation probability about the UC. So first of all, the conclusion is collecting eye tracking data greatly helps, and it extrapolates across users. You can see that for HMM, Hidden Markov Model with eye tracking data and user browsing data, it can get a UC 0.82. And this is greatly bigger than this training with only browsing data. HMM is 0.69. And HMM is better than linear models. You can see that the linear model with eye tracking data is 0.75. This action stats, that's a simple baseline, which is basically assigning the fixation probability according to the action probability in your history data set. Assign that dwell time. So the second set of results, MAE, lower is better. With similar result, collecting eye tracking data significantly helps, extrapolates across users. You can see that the lowest one is 0.332. It's in seconds. And also, however, hurdle linear model is better than HMM here. And this might reflect that the problem with the generative modeling because it made a lot of strong assumptions. And for those who are curious, R square is 21%. Some think these are good, some are not, some do not. But I will just show this number to you. And so this is a set of a specific result here. This is about the gaze behavior on this grid layout. So there are two theories about this attention in previous research. F pattern basically means going from top to bottom, left to right, the fixation probability continually decreases. And there's another competing theory that is the center effect. Basically, if you have a picture, the center part will have a higher fixation probability. But here, our results supports the first theory, F pattern. You can see that. Actually, there's a caveat here. The first row, the second row, and the first column and second column are not significantly different. But starting from the third row and third column, it continues decreasing. So these are the messages from this talk. Gaze prediction extrapolates across users. This is a good message. Collecting eye tracking data from a small number of users greatly help to predict other users. Potentially, you can use this to predict other users in your whole system. Applying the right models makes a significant difference. HMM is better for fixation probability, hurdle linear models for fixation time. And our data supports F pattern instead of a center effect. They might because of the structure in this interface. It's a matrix, and it has rows and columns. This structure dominates the gestalt view, I think, about the whole picture, because the center effect is usually present if you have an overall picture there. That's it. And you can check the paper for more results on other HMM models and prediction for other user tasks. And with that, I conclude my talk. Thank you. Any question?
Hey, thanks for the talk. You didn't mention it, and you said that there are more details on the paper, but the devices you dealt with, I assume, were desktop devices?
Oh, yeah, it is a desktop device. So it's a Tobii eye tracker. It has a set. It's actually fixed the screen size.
Mm-hmm,
right.
Mm-hmm. And how do you think this generalizes, if at all, to mobile devices where, the setups that you showed in the beginning of the talk, usually you don't have rows with items, and, usually it's just one column setup. Is it relevant for mobile devices?
I would say if you have a mobile device, actually, it's a much easier task compared with this one, because you can see the video I showed you is basically random walking with some statistical behavior behind it. But for a mobile device, if it has only one column, you can basically track the viewport of from the browser. You can get much better results on that task, I think. Right.
And one quick follow-up regarding the HMM models. Do you have intuition why they worked so much better than the linear models? What did they capture?
I think I think it captures better through Bayesian inference on the inside of giving that you observe action, what is the probability surrounding that position? Because this is a good fit for that generative process. And that's why. But you may notice that actually in fixation time, it's doing a really bad job for HMM. I think it has some space, maybe big space for improvement. First of all, the HMM made a very strong assumption on self-transitioning, because this is a problem. When we split that time, that's the total dwell time into constant time intervals, we have to make decisions on how long it is. And it doesn't model the self-transitioning. I know there's a kind of a updated or advanced version of HMM, is like HSMM, Hidden Markov Model. It directly models the self-transitioning or duration on that fixation. It might greatly improve the fixation time, but it takes further study on that.
So, hello. Did you test the prior knowledge that the users could have about the task?
You mean how different in terms of different tasks, or?
I mean, are you assuming that all the subjects that you work with have the same prior knowledge?
Exactly. So basically, you can see that from the model we use an uninformative prior. We do not have a prior at all. And I think it might be better to have a user better prior. It could be, because you can check the paper for different tasks in different modes. Users' behaviors, gaze behavior are quite different. We have some results on that as well in the paper.
Okay, I think my question is somewhat rather like comments that I noticed that as one of your conclusion, it's a kind of the F-shape, F-pattern instead of central effect. I think that's really quite similar to the previous study on the web search behavior, on the gaze prediction, and also quite a lot of work has been made down on the eye tracking data on web search. So I think that would be really interesting to compare the user's behavior between web search and recommendation. Right. Actually, I expect that they should be totally different, but a little bit surprised that there seems no quite significant differences that according to your result.
Okay, I am glad to hear that. Thank you.
I just have one question, and
okay.
Maybe that's a silly question, so I apologize if I missed something. But if you look at previous literature in the field of eye tracking, especially what Wendell wrote, you see that eye tracking depends on contrasts, for instance, on certain shapes. So there is a dependency on what you show. Have you taken that into account when showing the different pictures?
Right. That's a great question. So for visual properties or those bottom mechanism, I mentioned that top-down versus bottom. We do not use that, any feature from that. And I do have an argument, but I'm not sure whether you buy it or not. So there are a lot of research have shown that those top-down approach, cognitive tasks, we have control on our everyday tasks. Those are more important to predict. And those saliency bottom approach, from the research, we have some related work. If you can check the paper for that. And I basically agree with that. But we'll see. And probably we need to further study on this, probably incorporate visual property and compare and to do further study on this. But I totally agree, this is an important aspect to look at as well in the future. Right. Thank you.